This video is based on a presentation given at the Federal University of Rio de Janeiro in 2025, in collaboration with Dr. Nobuo Toride and Dr. Rian von Genugten. My name is Seki, from Toyo University, Japan. Today, I'll be discussing these two papers. Both works focus on representing multimodal soil hydraulic properties. The first paper, published in the Vados Zone Journal, emphasizes model development, while the second, published in the Journal of Hydrology and Hydromechanics, focuses on model evaluation. In this presentation, I will omit the technical details and concentrate on the main findings. Dr. Derner proposed a multimodal water retention function. In this function, S of H represents the effective saturation and is expressed as a linear combination of van Genugten models, each serving as a sub-retention function. In this figure, a bimodal function is used, resulting in two distinct peaks in the pore size distribution. Our model extends Derner's approach by incorporating a variety of unimodal models. As shown in this table, we selected three models as sub-retention functions, S sub I of H. BC refers to the Brooks and Corey model, VG to the van Genugten model, and KO to the Kosugi model. Any combination of these models can be used. As illustrated in this figure, combining two BC models yields a dual BC model. Similarly, we can construct dual VG and dual KO models. The notation VG1 BC2 indicates that the VG model is used for the first subfunction and the BC model for the second. This is the water retention curve of a Japanese andesol, which is highly aggregated. The bimodality of the pore system is well captured by the first and second subfunctions. All of these models fit the data well, with R-squared values greater than 0.99. Now, I will discuss the unsaturated hydraulic conductivity function. The general form of this function is shown here. It generalizes the Burdine and Mualem models by introducing the parameters P, Q, and R. For specific values of these parameters, the equation reduces to the original Burdine or Mualem model. Since this equation includes an integral, analytical solutions were derived. I won't go into the details in this presentation, but in our paper, you can easily find closed-form solutions for any combination of sub-retention functions. At the bottom of this figure, hydraulic conductivity is plotted using the Mualem equation for each of the four models. The resulting conductivity curves show similar shapes. The multimoding model can be simplified using the CH model. CH stands for constant head, where the parameters HBI for the Brooks and Corey model, 1 over alpha I for the van Genugten model, and HMI for the Kosugi model are all set to the same value, H. For sandy soil, as shown in this figure, the CH model fits the water retention data very well. The models used in our study, dual BC-CH, dual VG-CH, and VG1 BC2CH are compared with the FS model, Fayer and Simmons. For all models, the hydraulic conductivity curves computed with the Mualem equation are very similar. In fact, Nobuo's colleague, Sakai, has previously shown that water and vapor movement in this sand can be accurately simulated using the FS model combined with the Mualem equation. Therefore, by producing a similar curve, we demonstrate that our model is also effective in this context. Now I will talk about our second paper, published in the Journal of Hydrology and Hydromechanics. We demonstrated the practical utility of multimodal equations by evaluating three models: DBC, which refers to dual BCCH, DVC, which is dual VGCH, and KBC, which is KO1BC2CH. For comparison, the Peters model was used. Parameter optimization was conducted in two steps. First, we optimized the water retention parameters. Then we optimized the saturated hydraulic conductivity and two parameters from PQR in the general hydraulic conductivity equation. While typically only the tortuosity factor P is optimized, with Q and R fixed, we showed that optimizing two parameters improves performance. Therefore, we fixed one parameter in PQR. In the Van Geenuchten model, since the water retention function includes Q, we fixed Q equals 1 and optimized P and R. For the DBC and KBC models, we fixed R equals 1 and optimized P and Q. For Gillotte loam soil, as shown in this figure, we achieved excellent fits to both water retention and hydraulic conductivity data using the DBC, DVC, and KBC models, as well as the Peters model. This demonstrates that our models offer flexibility comparable to the Peters model.
So, why do we need to optimize two parameters? This figure shows a sensitivity analysis of RMSE with respect to the parameters P and Q. The minimum RMSE occurs at P equals 6.4 and Q equals 0.1. If we fix Q equals 1, for example, the RMSE does not decrease sufficiently. The middle panel shows the case for the KBC model, where R is fixed at 1. In the upper two panels, where Q equals 2 and Q equals 1, adjusting only the tortuosity factor P is not enough to fit the entire hydraulic hydrativity curve. In contrast, in the bottom panel, where Q equals 0.1, the curve fits well when P is optimized to 6.4. The rightmost panel shows a similar trend. This example is for the dual Van Geenuchten-CH model with Q fixed at 1. In this case, R equals 2 corresponds to the Multimodal model, but the fit is poor. However, when R equals 0.1, the curve fits very well. These results demonstrate that two parameters, either P and Q or P and R, should be optimized simultaneously to achieve the best performance.
So why do we need two parameters? Again, from the analytical solution of the Multi-Brooks-Corey model, the slopes of the ith subcurve can be expressed using this equation. Here, lambda I represents the slope of the log-log plot of the water retention curve, and AI represents the slope of the log-log plot of the hydraulic conductivity curve. Both lambda and A are positive values.
Therefore, in the case of I equals 2, the points lambda I, AI lie on a straight line in the lambda I plane, as shown in this figure. This figure is based on the same soil used in the previous slide. The slope of the red line is P plus R, and the y-intercept is QR. For the Multimodal and Burdine models, QR equals 2, which means the points cannot lie on both lambda 1, A1 and lambda 2, A2 simultaneously. In this case, we can only optimize to lambda 1, A1, as indicated by the blue dotted line. Therefore, when we have the same values of P plus R and QR, similar hydraulic conductivity curves are obtained. Just look at this figure. It shows different values for P, Q, R, but with the same values of P plus R and QR. As you can see, all the curves are very similar. This demonstrates that simultaneously optimizing all three parameters, P, Q, R, is actually unnecessary, and it makes more sense to fix one parameter, either Q or R. We also tested our approach on 20 soil samples from the UN SODA database and found good agreement between our predictions and the measured water retention and hydraulic conductivity data across a wide range of pressure heads. Here are two examples. The unimodal Van Geenuchten model underestimates hydraulic conductivity at high matrix potentials, whereas all the bimodal models successfully fit both the water retention and hydraulic conductivity curves. Here are the R-squared values for all models and samples. As you can see,
Most of them show very high values. In particular, the DVC and KBC models perform exceptionally well. Now I will talk about a program that I developed. To write the papers I mentioned earlier, I created a Python library called unsatfit, which is designed to optimize parameters of soil hydraulic property functions. It was developed to systematically evaluate various hydraulic models and datasets using different optimization methods, including the selection of constant and initial parameters. This is a screenshot of the website. It contains comprehensive documentation. The unsatfit website provides sample code that demonstrates how to calculate parameters from measured data and generate fitting curves following the same methodology described in our papers. By visiting the sample code page, you can download the code and follow the instructions provided there. We also developed a web application called SWRC Fit, which generates soil water retention curves using various soil hydraulic models from measured data with just a single click. The application is built on the Python library unsatfit and simplifies the process of determining water retention parameters by eliminating the need to select initial parameter sets. You simply select the models you want to fit, input your water retention data in the text area, and click the Calculate button. Then, you'll quickly receive the calculation results, like this. This shows the list of fitted models, equations, parameters, R-squared values, and AIC values. The fitted curves are also displayed, as shown in the right panel. Finally, I'd like to briefly introduce my work on the optimization of the dual VG model, which I published in a Japanese journal. The algorithm for fitting water retention curves for the dual VG model has been improved. I demonstrated that its fitting performance for various Japanese soils and UNSOD soils was comparable to that of global optimization methods. This figure on the right compares the fitting performance of our method with that of the global optimization method. This algorithm is already implemented in the programs I introduced in the previous slides, so you can easily use it with my software. We extended Dörner's model to incorporate linearly superposed subretention functions using any combination of the BC, VG, and KO water retention models. We demonstrated the practical utility of these equations for evaluating both water retention and hydraulic conductivity functions by testing them with various soils. Optimization of two parameters, P plus R and QR, in the general hydraulic conductivity function is required for multimodal models. The calculation code is freely available to everyone. The URL for the program is provided in the YouTube description. That concludes my presentation. Thank you.